Right now, inside a climate-controlled server facility on the outskirts of Hangzhou, China, thousands of black rectangular circuit boards are crunching trillions of mathematical operations per second. They are training advanced artificial intelligence models, processing human language, and running autonomous systems. But if you were to open the server chassis and pull out the primary processor, you would not see the logo of Nvidia or AMD. You would see a stylized logo depicting a Precambrian geological explosion, and a name that almost no one in the Western world was paying attention to 2 years ago: Cambricon. In a single fiscal year, while targeted by the most stringent export controls in human history, this company's revenue surged by more than 450%. It did not just survive being placed on the United States Entity List. It turned its first-ever clean annual profit, driving its market valuation past $40 billion. That is not a metaphor. That is just the financial math recorded on the Shanghai Stock Exchange's Star Market for 3 years. The dominant global narrative around artificial intelligence chips was simple: cut off China's access to silicon wafers printed in Taiwan. Deny them extreme ultraviolet lithography machines from the Netherlands, and their AI ambitions would hit a brick wall. But right now, today, in 2026, Chinese tech giants are not stopping. They are buying tens of thousands of domestic AI accelerators designed by a company that was once dismissed by Western analysts as a money-losing academic experiment. Hit the like button and subscribe. It genuinely helps the channel bring you these deep technical breakdowns. And let's get into how this happened. To understand why Cambricon's sudden profitability is shocking the semiconductor industry, you have to understand the sheer scale of the global dependence on a single company, Nvidia. For the past decade, the entire modern artificial intelligence revolution has run on GPUs, graphics processing units that were originally designed to render 3D video games. Nvidia's founder, Jensen Huang, made a multi-billion-dollar gamble in 2006 by creating CUDA, a software platform that allowed programmers to treat a graphics card like a massive parallel supercomputer. Instead of running 2 or 3 complex calculations very fast on a central processing unit, or CPU, a GPU runs tens of thousands of simple matrix multiplications simultaneously. When modern deep learning emerged, CUDA was the only fully developed language ready to run it. By 2022, Nvidia controlled more than 90% of the global market for AI training chips. Their flagship processors, the A100, the H100, and later the Blackwell architectures, became the crack cocaine of Silicon Valley. A single server rack filled with H100s could cost upwards of $300,000, yet tech companies lined up in queues that stretched out for 18 months. The reason was simple. Nvidia chips offered unbeatable memory bandwidth and a software ecosystem so deeply entrenched that every AI researcher on Earth wrote code designed specifically for CUDA. But this created a systemic vulnerability. Just as a nation relying on oil imported through a single maritime strait faces a geopolitical bottleneck, the entire global AI economy became dependent on a single supply chain. Designed in Santa Clara, manufactured in Hsinchu by TSMC, and packaged using advanced three-dimensional stacking technologies called CoWoS. When the United States Department of Commerce issued sweeping export controls in October 2022 and updated them in late 2023, the goal was surgical. By banning the export of any chip with an interconnect bandwidth exceeding 600 gigabytes per second, or a total processing performance above a specific threshold, Washington effectively cut off Chinese AI companies from buying H100s and B200s. The assumption was clear. Without access to the world's most advanced silicon, China's artificial intelligence sector would stall out on legacy hardware. This felt like a problem with no real engineering solution, until Chinese hyperscalers were forced to look inside their own borders. Before its sudden explosion in market share, Cambricon was not viewed as a serious threat to Western tech giants. Founded in 2016 by two brilliant brothers, Shen Yunji and Shen Tianxi, researchers at the Institute of Computing Technology within the Chinese Academy of Sciences, the company began as a purely academic endeavor. They named it after the Cambrian explosion, the geological era 500 million years ago, when biological diversity on Earth suddenly exploded. Their core thesis was radical. Graphics processing units were fundamentally inefficient for neural networks because they still carried decades of legacy baggage from rendering 3D graphics. Instead of adapting a gaming chip for AI, they wanted to build a native domain-specific architecture, a chip built solely to calculate matrix math and nothing else. In 2016, they released a paper detailing Dian-Nao, the Chinese word for computer, literally translating to electric brain, which won prestigious architecture awards in the West. Huawei took notice and licensed Cambricon's early IP to create the neural processing unit inside the Kirin 970 smartphone processor. For a moment, Cambricon was the darling of Chinese tech. But then, the real world intervened. As Huawei grew its own internal chip design division, HiSilicon, it stopped licensing Cambricon's designs, opting to build its own Ascend architecture instead. Cambricon lost its largest customer overnight. Between 2017 and 2022, the company bled cash. They spent hundreds of millions of dollars attempting to design enterprise-grade data center chips, but Chinese cloud giants like Alibaba, Tencent, and Baidu refused to buy them in scale. Why would an engineer at Alibaba rewrite their entire software stack to run on an unproven Chinese chip when they could simply rent or buy Nvidia A100s that worked seamlessly out of the box? Western industry observers gave Cambricon a dismissive nickname: the academic money pit. Critics pointed out that the company spent more on research and development than it made in total sales, surviving almost entirely on local government subsidies and public stock listings. Their chips suffered from three brutal, concrete weaknesses. First, their memory bandwidth was too narrow to feed modern large language models. Second, their software SDK was clunky, requiring manual optimization by hand-coding CUDA equivalents. And third, their yields at commercial foundries were uncertain. It was the classic chicken and egg problem of technology. Without customers, you can't improve your software, and without good software, you can't get customers. The turning point did not come from a magic breakthrough in chemistry or lithography. It came from a fundamental reframe in how chip architecture handles artificial intelligence workloads. When the US bans shut off the tap of Nvidia hardware, Chinese software engineers could no longer rely on brute force hardware power. They had to look at how chips actually execute matrix math at the silicon level. In a traditional GPU, a vast amount of physical die area and electrical power is wasted on cache coherency, instruction decoding, and control logic meant to handle unpredictable software loops. Cambricon's engineering team realized that modern large language models, specifically transformer architectures, do not perform unpredictable loops. They perform predictable massive-scale matrix multiplications interleaved with specific activation functions. Here is how their breakthrough architecture, known as the SMLU, or Super Matrix Logic Unit, actually works in plain physical terms. Step 1. Instead of using a generalized register file, Cambricon built custom tensor processing cores integrated directly with a high-density, low-latency distributed on-chip SRAM matrix. Instead of fetching data from external memory over and over, which consumes over 80% of a chip's power, the weights of the neural network are staged directly adjacent to the arithmetic logic. Units! Step 2. SMLU bypasses standard vector pipelines by implementing a direct-mapped hardware systolic array. Imagine a grid of simple digital calculators organized in a two-dimensional matrix. Data flows through this grid like water through an ice cube tray. Numbers flow from left to right. Weights flow from top to bottom. And at every intersection point, a multiply-accumulate operation happens in a single clock cycle without writing intermediate results back to main memory. Step 3. to solve the memory bottleneck without access to forbidden foreign high-bandwidth memory, Cambricon redesigned their memory controller to use ultra-wide 1024-bit interfaces paired with custom interposer routing, allowing them to stack standard, non-sanctioned memory modules in a way that emulates high-end HBM speeds. And here is the brilliant part. The old software weakness did not get fixed by magically writing 10 million lines of code overnight. It was rendered obsolete by the open-source AI community. In late 2023 and early 2024, frameworks like PyTorch and Triton matured. Triton, an open-source GPU programming language created by OpenAI, decoupled the software layer from Nvidia's proprietary CUDA language. Suddenly, a developer could write high-level AI code, and Triton would compile it directly down to Cambricon's native instruction set. The CUDA moat, Nvidia's greatest defense mechanism, was bridged not by Cambricon, but by the global open-source ecosystem trying to break Nvidia's monopoly. Theory is fine in an academic paper, but in the semiconductor industry, real-world deployment is the only metric that matters. In mid-2024, rumors began circulating in foreign financial markets that a mysterious Chinese AI research lab named DeepSeek had trained a world-class open-source language model at a fraction of the cost incurred by OpenAI, or Meta. While Western analysts assumed DeepSeek was secretly using smuggled Nvidia H100s, state procurement records and local disclosures revealed a far more complex reality. DeepSeek, along with major Chinese cloud operators, had deployed massive clusters utilizing domestic chips, including Cambricon's CE series and SMLU-based accelerators. In the Lingang special area of Shanghai's Free Trade Zone, a massive new AI computing cluster came online. Spread across 3 football fields of server racks, the facility houses over 20,000 domestically produced AI accelerator nodes. Monitored trial data from the facility demonstrated that for inference tasks, the phase where an AI model answers user questions rather than learning from scratch, Cambricon's latest chips achieved up to 82% of the throughput of an Nvidia H100 at less than half the operating cost. To make this happen, Cambricon had to pivot its entire manufacturing strategy. When TSMC was forced to stop printing advanced chips for Chinese designers, Cambricon worked closely with Semiconductor Manufacturing International Corporation, or SMIC, China's premier domestic semiconductor foundry. By using SIMI's advanced N+2 process node, a sophisticated 7-nanometer equivalent process that utilizes multiple patterning deep ultraviolet, or DUV, lithography, Cambricon re-engineered its physical chip layouts. They made the physical silicon dies larger, using advanced chiplet packaging, where 2 smaller silicon dies are fused together on a silicon interposer to bypass the physical yield limitations of printing one giant chip. The financial results were staggering. In its latest earnings filings on the Shanghai Exchange, Cambricon reported annual revenues scaling by over 450%, crossing 4 billion yuan, with net profits turning positive for the first time in the company's decade-long history. State-backed infrastructure funds, local municipal governments building smart city data centers, and domestic tech firms like ByteDance and China Telecom signed multi-year supply contracts. But here is the honest part of this story, the technical reality that hyper-bullish headlines routinely ignore. None of this means that Cambricon has magically erased the gap between Chinese chip manufacturing and the rest of the world. The physics of semiconductor fabrication are unforgiving, and Cambricon operates under severe structural constraints that will not disappear overnight. The first major hurdle is raw silicon yield and thermal dissipation. Because SMIC is forced to use DUV lithography with multiple exposure passes to print 7-nanometer feature sizes, a process that ASML's EUV machines perform in a single pass, the defect density on every silicon wafer is significantly higher. Industry estimates suggest that the yield rate for complex large die AI chips at CIMIC hovers between 40 and 60%, compared to over 85% for TSMC's 4-nanometer lines. Every failed die drives up the net cost of the surviving chips. To compensate for process nodes that are physically larger than Nvidia's 4-nanometer Blackwell architecture, Cambricon engineers must pump more electrical voltage through the silicon to achieve comparable clock speeds. That creates a massive thermal energy problem. A Cambricon server node running at peak workload can draw up to 20 to 30% more power per unit of compute than its Western counterpart. That extra power translates directly into extreme heat, requiring complex, expensive liquid cooling systems in data centers that raise the overall cost of ownership. The second structural bottleneck is advanced packaging. Even if SMIC can print enough compute dies, fusing those dies with high-density memory requires advanced silicon interposers and micro-bump packaging, a domestic capacity in China that is currently severely oversubscribed. Huawei, Cambricon, Byron, and more threads are all competing for the exact same domestic packaging lines. There is a physical limit to how many server cards Cambricon can deliver per month, regardless of how high their order books pile up. This is not a story of instant total victory. It is a story of grinding, highly expensive brute force engineering designed to survive an embargo. Which brings us back to the bigger picture this whole story has been building toward. For 30 years, the global technology sector operated on a single unified architecture. The world shared one software standard, one dominant GPU vendor, and one primary foundry in Taiwan. The export controls imposed by Washington were designed to preserve that monopoly and maintain a technological moat. But the law of unintended consequences is taking effect in real time. By cutting off Chinese companies from foreign silicon, the sanctions eliminated the economic risk that previously prevented Chinese tech giants from buying local hardware. In 2021, buying a Cambricon chip was a career risk for a Chinese software manager. In 2026, buying domestic silicon is a national imperative backed by unlimited state capital and guaranteed corporate demand. The result is the bifurcation of global computing. The world is splitting into two parallel technology ecosystems. One runs on proprietary, highly polished Nvidia hardware and CUDA software backed by Western venture capital. The other is a scrappy, highly optimized, open-source-driven ecosystem running on domestic Chinese silicon, like Cambricon and Huawei Ascend. Forced by necessity to innovate at the architectural level rather than relying purely on smaller transistor sizes. The assumption that you can permanently freeze a nation of 1.4 billion people, producing more STEM graduates per year than the rest of the OECD combined, out of a crucial technology by controlling supply chains has been challenged. Cambricon's rise from a money-losing science project to a profitable, multi-billion-dollar silicon powerhouse is proof that when you block a river, the water does not simply stop flowing. It builds up pressure until it cuts a completely new channel through the rock. The Silicon War is no longer about whether China can make AI chips. It is about how fast those chips will improve when millions of developers are forced to use them every single day. Which leaves us with one critical question. As open-source software continues to strip away Nvidia's software advantage, what happens to Western tech dominance when Chinese chips become not just good enough under sanctions, but cheaper and more abundant than anything produced in the West? Let me know your thoughts in the comments below, and don't forget to like and subscribe.